Good morning, everyone. Welcome to the second International Conference on Pattern Recognition and Artificial Intelligence. This morning, I'm very pleased to have Professor David Zhang, Presidential Chair Professor of the Chinese University in Shenzhen. He is the Director of the Research Center of the Institute of Artificial Intelligence and Robotics. He is a Life Fellow of the International Association for Pattern Recognition and will soon become the Fellow of the Royal Society of Canada. So Professor Zhang. So I will stop the share. You can share now.
Okay. Thank you for your introduction. And actually, I'm very happy to report our research. Today I would like to talk about that is advanced biometric research and development. And I think a few subtopics, we'll deal with. First one is we talk about that why is biometric? Because maybe someone is maybe not familiar about that. Actually, is biometric is depend on is human being. How to identify. So usually we have two traditional method is what you know, just like a password, what you have, like the ID card, but both maybe have some problem. So this is the reason is why we use the biometric, because of more accuracy and safety. But since the biometric is necessary, and basically is biometric is we can give some description, just like any two person is not exactly the same. So this meaning is each person should have unique feature. So what are the feature we can find from each person? So maybe we can find is physical feature. So what you are, like a fingerprint, a face, and so on. So maybe you have behavior feature, signature, voice, and gait, and so on. So using this different feature, we can extract from each person, then we can get its biometric and data and for the security applications. And so far, is biometric is very hot. Because since September 11 is we can find the market share is very good. And if you look at the market share, we can find is a few biometric is take and more part, like the fingerprint is maybe and based on is point feature, but a face based on geometry feature. Also for the iris and based on its text feature. So I think this is belong to the physical feature is maybe take more and part, percent is in the market. But if we work on its biometric research, we still think is this different the biometric even very popular, but still have some problem. So here we just list for fingerprint, even have 100-year history, but we can find is some fingerprint, maybe not good quality of image. So some maybe change, is depend on aging. And so this is meaning is even some person cannot find its fingerprint, its minutiae feature. So this is have some this problem. And since is fingerprint, everybody have this fingerprint, but roughly have 5% person cannot have not good quality of image, because maybe some people is older guy is so dry, okay, maybe some people is a hard worker is so smooth, okay, and also is fingerprint have other problem is touch on the sensor, so sometimes left something on the sensor, so this is maybe is not safety. And other problem is fingerprint, okay, using this method, okay, then we can, using the 10 minutes, we can make any fingerprint is mark, okay. So using the mark, and Hong Kong and the government, okay, set up is e-channel, so totally, and using the 400 million in the Hong Kong dollar and get e-channel, but some, okay, and for the iris, okay, it still have some problem. It's we just list here is if iris, okay, is basically is from the original find iris can do the personal identification from the doctor, but we can find the different the disease from the iris. So this is difficult can get is good iris image, and also problem is for and if we and get printed, okay, iris, okay, also is get some the new, okay, like the fake iris, okay, using the synthesis, but difficult to recognize it's real and is something is wrong, okay. So here is just we go to the website is using the contact line, okay, is UK government, okay, pay is 9 million is and is dollar, okay, is for and iris is using the airport, okay, safety, but final is have some problem, is cannot use again, okay. So this is the problem is because iris maybe and difficult recognize real or not, and also find is and takes time to longer than the human being to do, okay. So what is next? Okay, so this is for this presentation we talk about that is advanced biometric is basically is we can find new methodology, new technology, and a new system. Okay, then we can create is new direction, and also is explore is new result. So this is we report is our first research is palm print authentication. So palm print still is from the human being is hand. Then we can call this part is palm. Okay. Then we can find this part have more feature inside. So we can find geometry feature and text feature, line feature. Even we have some many minutia feature, exactly like the fingerprint. And also palm, okay, palm here we also find some the blood feature. So this is compare about that fingerprint, face, okay, iris cannot. Okay, so this meaning is palm print is more feature, also more safety. Okay, so compare about that is other is we also think palm print is have some good performance. So this is here just we test is the same person over 5 years is still no change. So this meaning palm print still we can take this as the personal identification, a unique feature. And the other is using the twin. We correct is a few hundred twin is we can 100% can easy to separate. And also is palm print is have other advantage is maybe we call and robot, okay, is because if we put some is dirty on the palm, okay, is still we can get a good result because palm print is a larger area, is even have a small part, not like a fingerprint, is very small, and the palm print is larger enough. Then if we have some dirty, still we can can recognize. So this is palm print is other advantage. And 2004, okay, is palm print is the first time listed as the one member of the biometric family. And then after that, we still think palm print have compared with other. Okay, we can find good algorithm. So this is we test about that is a few and the popular palm print algorithm. Okay, is except ours. We can find other is working team. Okay, and final we think our algorithm still good enough. Okay, and also we compare about that is the fingerprint, iris, and face. Okay, using the public database. Okay, and then we using the palm print. We think about that is accuracy is good enough. Okay, and so far, okay, we developed palm print is different. The version is we can compare 3D and palm print system, multi-spectrum system, and palm print plus fingerprint and plus Win and so on. Okay, then we focus about that touch and the touch rate. Okay, is different the palm print system. Okay, we have different demo to show. Okay, and so far palm print is got more is pattern. Okay, is also is have good publication. Is different the algorithm. Okay, and also is award. And this is the first palm print is published in 1998. This is the first in the actually is the first palm print paper in the world. And also we published the 2 books is relative the palm print. Okay, and second is we call is medical biometric, because this is we develop a second new development. So using this idea is we just think about that is human body outside. Okay, we can take using different measurement, we can find the problem. Just like we can take a look at the face, okay, and find some the tongue and the odor, and even using the ECG and the EEG and so on. Okay, so this meaning is using the person outside and the body. Okay, we can measure human body inside any problem. So using this idea, we compare about that is our biometric technology with the medicine application. Okay, and actually here is we call TCM, the traditional Chinese medicine, just using the human body to judge about that different problem. And but TCM main, okay, even we have few thousand the history, but still have some problem is maybe depend on the doctor is knowledge, okay, is all the experience. So how to make is TCM get some the modern, okay, everybody understand easy. Okay, so this is our job, is combining its biometric with its TCM. But so far, okay, we can find is expert system. So this is and using the AI, artificial intelligence, work with the TCM doctor, then get some rule, and final using the rule get to the diagnosis. But we believe about that using the expert system cannot, okay, make the TCM is real, is easy to understanding, because sometimes is maybe not get a good and result. And our method, okay, is we call medical biometric. Its meaning is using the biometric technology, okay. Also we collect is larger database, okay, and work with expert is doctor and work together. Then we can find and the different the disease is a feature, and using the feature we can do the diagnosis. So we call different from before. We call is data driven, okay. And after that we find is for human being outside. then we can measure the different part. Okay, maybe visual sensing and auditory sensing and olfactory sensing and tactile sensing. Okay, and now we just basically talk about that using the visual. Okay, perception. We work on the tongue as the typical and the example, and we develop its device, collect a larger database from the hospital, and then using the color feature. And we first one using the how to make a color is standard. Okay, so this is we using the color checker. Okay, final we can find is different just a camera, different lighting. Final after the color checking. Okay, then we can get the similar and standard color image. And also is using the segmentation. Okay, is for tongue is how to extract from the background, and we can use the different method. Okay, here we just talk about that is using the two different methods combining together. Final, we can get a good result. Okay, and for tongue feature, okay, is we can extract a different feature. Basically, we have 5 different features. Okay, first feature is color feature, and here you just talk about that is how to get a color. Okay, and after we collect a larger database, okay, from the different hospital and of the different disease, then we can put together, get some just like tongue color subspace. Okay, and using the subspace, then we can find the cluster. And the final is we can using 12 different color and component standard for the tongue color. Okay, so after that, okay, we can do is coating and substance. Okay, separate, because we have is coating color 4 and substance is 8. Totally we have 12 color components. So easy to separate these 2 different class. And also is we can using the color find some reflection point. Okay, and also is dark point. And also we can find the tongue have some red point. Okay, depend on is red point is age on the tongue. Okay, then we can find different position, get some different analysis, and then we can roughly separate tongue is have 6 different shape. Okay, and using the geometry feature, we can get some roughly and classification. Okay, and after that, okay, we also using the texture feature. We can find inside the tongue maybe have some more detail. Okay, so this is using is the text feature. We can find some typical and example. Okay. And also we find the tongue and have other feature we call crack feature. Okay, so this crack feature is maybe and have normal and non-normal. Okay, and then we can roughly can get some result. If non-normal, okay, maybe not real healthy. So this is roughly we can get is this result. And after that, okay, we can use all the feature we extract, then do the diagnosis. Okay, this is the first paper is tell about that we give 3 different class. Okay, then using the color feature, okay, then we can separate each other. Okay, and after that we can more and more data we can correct. Then we can separate is yield and sub-healthy, healthy, and even have the yield and water problem. Okay, so using the different feature do some classification. Okay, so this is just our publication is recently is we have published the tongue and image analysis by the Springer, and then also we have more and more paper to published. From the first paper is 2004, and each year we have some new contribution. Okay, and for olfactory, okay, is perception. We basically take some breath, okay, is signal analysis. So breath is we design is a device and people do the breath, then we can get some the inside is chemistry and the component and find out is which problem. So we take this device, go to the hospital, then we can find different disease, okay, different class have different performance, okay. And after that is we also test about that same person, okay, do the different the treatment before and after, and then we can find is visual form can change, okay. So this meaning is our the device is sensitive to some chemistry and the component. So using its biometric technology, we still extract all the feature we can, okay, then do different the classification, okay. So this is we got the project from Hong Kong government is using the brand using our device, okay, to easy to test about that diabetic, okay, because before diabetic is using the blood, okay, is harmful and maybe people not like to do. But now is we know diabetic maybe using the blood, okay, but also maybe we can use the breath, okay. So then after using the breath, then we can test about that. Even any person the breath, okay, is then we can check about that is diabetic or not, okay, is using is our system, we can separate is different level, okay. So this work, okay, is still we work on is continue, okay, is we also have some the paper recently is one is electronic notes, okay, other one is breath analysis for the medicine application, both published in the spring, okay. And a third one we call is touch. Touch is a typical and sensing, okay, using the pulse waveform. So this is we can design our device, okay, and then using that we can measure and the human being pulse, okay, this device do about that. And finally, we can get different the waveform. So after that, we can go to the hospital to test about that our system. So this here tell about that different the disease have different the performance. And after that, we compare about that ECG, because ECG still measure is the human body is heart, but the pulse is a different part, because the ECG is basically is directly is heart, okay. But the if blood pass through inside all the organ, okay, go to the end of the part like some the hand, okay, is then we can find here is should be more information compare about that ECG. So this is we using our device ECG work together. Then we can find ECG, okay, and our pulse device waveform, okay. Then we can find is ECG is more information inside in the waveform, okay. And also we find some is disease ECG not easy to separate, but using our the pulse, okay, and we still can get high and good result, okay. And this is just using the biometric technology. We extract all the feature we can. After that is we can give some different class, okay. Then we can do some different the result. Final is we just show about that is 2017, okay. We also have some the new book is computational pulse signal analysis published is spring, okay. Also is more and more publication journal paper. First paper is 2003, okay. Then each year we can find some our contribution. Okay, and final is we call is hearing, is auditory, is perception, because using the voice. Okay, so far is voice. We have two popular applications: is who talking, what is talking about that. But we have third application is when people talking, what is and medical information inside. Okay, then is we can design our system, go to the hospital to correct the data. Okay, here we just compare about that. Is healthy. Okay, is person with the disease. Okay, is maybe visual form is different. Okay, and also is we can find some. Okay, is a problem. Okay, maybe from is and nervous system, also maybe from the breath system. Okay, is even some other part. Okay, then we find out. Okay, this system may be a relative disease, maybe relative to the voice, and after that we collect is more and more data and compare about that. Okay, like Parkinson is a disease, like some cancer and something. Okay, and the final is we find is using the voice. Okay, we still think about that, can do some the measurement, do some the medical application. So this is recently. Okay, this year we published a new book is pathological voice analysis. Okay, is still published by the Springer. And now is if we have 4 different sensing. Okay, then how to combining together. So this is we call the fusion. And using the fusion, we will get higher and accuracy. So this is using the different part. Final using the fusion. Okay, and this is result should be better. Okay, is for the single one. And this is we have still working on, but we believe about that the future we have the more and good result is real and find out. Okay. And actually, for the medical biometric, basic idea just combining is medicine application plus is biometric. Okay, technology work together. So in the world, we open this direction. We have some a few and international conference on the medical biometric, and this is we published the book. Okay, is tell about that. What about the medical biometric? Okay, and this is published book in the 2015. Okay, and third one is how to using the biometric do the facial beauty analysis. So this is we open is third direction, because for the human being face, okay, using the face judgment, and we can do the identification. But also people using the face to still judge about that is how beauty about that. Okay, and we test about that is 2 different picture. Most of the people think about that. So this picture is more beauty. Okay, so this is the reason we want to find this common feature. Why is beauty? So this is our challenge. Okay, and now is using the biometric, and we set up the interface. Okay, and then you check the face, all the landmark. After that, we can change the landmark. Okay, get some different the face, and our research just find which one is more beauty. Okay, so this is using the beginning is we work on, and after that, okay, is we got this larger database from the 61 country and region. Okay, and after that, we want to get some the inside analysis. Okay, is find common facial beauty feature. Okay, and after we correct is some different feature. Okay, from the Eastern, Western about the facial beauty rule. Then we put together. Okay, totally we got the more the rule. Okay, then we find out is this rule is which rule. Okay, is more useful. Okay, special we can find out is new feature vector can do. Okay, is facial beauty analysis. And here just give you some result is using our current method. Okay, then we can measure our database is labor is beauty. Now, of course, this and people trust this should be beauty face. Okay, every example is satisfied its requirement, but a general person, okay, is normal person, maybe not. Okay, also is we using the data interface. Okay, we can do is find the different is algorithm. Okay, and then using that, okay, we can do the different analysis. Okay, do the criteria analysis. And here is just show about that our different method, like average method and Chinese method, okay, golden rule, and so on. Okay, final, we think about that using the fusion. Okay, using our method is combining is other method rule to find out is new and the fusion rule, and then we using that do the diagonal the facial beauty analysis, and from our database is top 32. Just we got this. Okay, so this is the last 32. Okay, then we can compare about that is top 32 real more beauty than the last 32. Okay, so of course is this only give you some basic experiment. Okay, and for beauty analysis is our new direction. Is we published the book is like we call the computer model for the facial beauty analysis. Is published in 1980. Okay. 2018, and also is we have more and more paper. It will appear later. Okay, and for 3 direction also is we can use is our new technology. Okay, and work with the biometric, get some the normal result. Okay, like some 3D biometric. So this is we develop is our, because biometric like fingerprint, face, and iris, tongue always is 3D. Okay, then we can using 3D different structure. Okay, then we can find out is optimal for each and the biometric applications. Final is we publish the book is 3D biometric. And also we think about that is biometric not only using the visible lighting, maybe some using the near infrared. Okay, and also we can use truth about that different spectrum. Okay, and after that we think about that this is a good topic, and we published our book is multi-spectral biometric. Okay, this is 2015. And then is we have some new development contribution is except the fingerprint, we have the minutia feature and the singular feature. Okay, and also we find 3D and the feature also is have some high resolution resolution of the convolution feature. Okay, so this using the Paul, okay, is get some new feature. So actually this is our new. Okay, so for that we have some the new book is published this year. Okay, and then is we develop is other different biometric like some the knuckle, finger knuckle, okay, print. Okay, then we put all different the development together, and we publish book is advanced biometric. So actually is we also using is our biometric and develop is different algorithm, find out is discrimination and the method. So this is we can publish different book. Okay, this is a latent book is 2016 is using the learning is biometric. Okay. And for our research is we call the Advanced Biometric Research Center. Basic idea is we hope have find using is high-level research. Okay, so this is we continue. Okay, 7 years to get some the highly cited researcher, and also is using the IT index. Okay, is 116. Okay, get some the roughly is 80 about the rank. Okay, and so this is our first guide. Okay, to follow. Second is we hope is our system is useful. Okay, so this is give some different demo, and after people is finished and thesis, then we can develop some new system and for the different applications. So this is our research, and I report here. Okay, thank you for your attention. Okay. Oh.
Thank you very much.
Okay, thank you for your attention. Okay.
Suen, we have a question. So she says, we assume that the background light may impact the colors of images a lot. If colors are considered as features in tongue analysis and disease diagnoses, how do you overcome this impact?
Okay, so actually it's color is special for color feature special for the tongue. Okay, because the tongue main feature is the color, and how to get some color feature is no change, because you know color maybe change different lighting. Okay, so how to make a color no change? Okay, then we real and takes time. Okay, to get some standard. Okay, using the lighting, also distance, and final is we can find out is different the color and the real, and get some different the problem from the tongue. So this is actually is if you are interested about that, and we have more and more paper relative to the tongue and the color feature, how to extract and how to matching to the color feature to the different disease. Okay, so this is actually is we work on the over 20 years. So everybody now is our team is to believe about that the color tongue color is real have some the can find out its disease and the problem. Okay.
Thank you very much. I don't see any other questions. And we thank Professor Zhang for such a comprehensive and complete studies on advanced biometrics. We appreciate it very much, and we admire your energy in this area. Thank you.
Okay, thank you. Thank you. Thank you. Thank you. And if you have any question, please touch with me directly. Okay. Thank you.
So the next, well, before we go to the next phase, I would like to inform all participants that proceedings of this conference is available at our website. Just click proceedings. Then you would have the entire proceedings published by Springer Verlag. And so the next one will be poster papers to be chaired by Nicola Nobili. And after that, we'll have 10 minutes break, and to be followed by another keynote speech. Nicola, it's all yours now.
Okay, thank you.
Okay, thanks for this opportunity to present our work at the second International Conference on PR and AI. Today, our topic is a new creative scoring model based on prediction of signal on graph. Study on high precision creative scoring model has become a challenge issue. In this paper, Our main idea is that the created scoring model can be mathematically formulated as a prediction model of the signal restriction problem on graph. As can be shown in this figure, firstly, we model the user and the relationship as a weighted and undirected graph. After feature extraction process has been done, we have part of non-neighborhood scores, and then our goal is to predict the unknown scores. This problem is ultimately formulated as an unconstrained optimization problem. The first term is used to ensure that the values of f is approximately equal to the known neighborhood scores. The last term, the regularization term, the transpose of f plus the Laplace matrix plus f, makes the solution be as smooth as possible. By using Fermat's representative theorem, we propose a new scheme, and in the reproducing color hyperspace. In the experiment part, we compare the results in UCI German credits dataset with some benchmark methods. Experimental results shows that our lower strategies have generated a very high prediction accuracy. Here is our brief introduction to this paper today, and thank you very much.
Hi, my name is Mohamed. Shenawy. I'm an assistant professor in Zhou City of Science and Technology, and this is our poster presentation for our paper submitted to the second international conference on pattern recognition and artificial intelligence. The title of the paper is Characterizing the Impact of Using Features Extracted from Pre-trained Models on the Quality of Video Captioning Sequence-to-Sequence Models. In this short video, I will talk about the main objective and key research questions we are trying to answer in this paper. I will also talk about, briefly talk about the approach, implementation, preliminary results, and future work. So the main objective is to build an efficient video captioning model, and what we mean by that is you have a machine learning model that takes video as an input and produces a number of sensible and reasonable statements describing this video as an output. To do that, you need a combination of features describing the object in the video, the scene itself, the activities going on, and also audio features. So let's say you have two persons in a room. So you need first to recognize that we have two persons, so a kind of object recognition, and then you need to recognize that they are in a room. And you need to recognize, for example, that one is sitting and the other is standing. You need to recognize what they are talking about, for instance. So this was the main research question. So what are the features that we can use? And can we use pre-trained models or transfer learning to extract those features? What is the right combination? How can we encode those features to have a better representation of the video? So this is the main questions we try to answer. So this paper is basically a work in progress that investigates the impact of using different features when we do video captioning sequence-to-sequence models. As the title indicates, we are using sequence-to-sequence. We are actually using encoder-decoder architecture, where we use LSTM cells to encode and decode the data. The model itself was based on a paper by Vernogopelen et al. In 2015. but we extended this model to add features about the scene, about the activities, about the audio, and so on. The final model has 4 stages: feature extraction stage, and then we have this stage where we project those extracted features into a fixed size feature vectors that is used as an input to the LSTM encoder-decoder network. And the third phase is the encoding stage, of course, and the fourth is the decoder stage. We used a different pre-trained model. We used ResNext 101 to extract the 2D object recognition features. We used ResNet 50 trained on Places 365 to recognize the scenes. We used Kinetics i3D model pre-trained on kinetic dataset to recognize the actions or the activities. We used SoundNet to extract the sound features. And the dataset we used is Microsoft Research Video to Text dataset, MSR-VTT. It has 10,000 video clips divided into 2 different categories, including music, sport, game, and news. The results, the initial results we have shows that using the features separately achieves the performance that is less than when we combine them together. So there is a value of using multimodal features. The initial result also does not show a big improvement in the performance when we add the sound features. We believe this is because a lot of the videos does not have conversation. So basically it's not actually affected by the sound. This is our kind of initial explanation of this. But you can see more details when you read the paper. We are currently working to improve this in many ways. First, we are looking for better methods to encode and reduce the size of the data, the input data to our model. We are also using better language models to generate the statements, and we are looking into trying different capacities of our model. So adding more nodes, for example. And we are studying the effect of increasing the capacity on the overall efficiency and accuracy of the model. Thank you for listening. If you have any questions, you can contact me on my email, shenawy@zuelcity.edu.eg. Thank you and bye.
Hello, my name is Jenifer and I'm from Korea University. Today I would like to introduce my research titled Prediction of Successful In-Memory Effects Using Convolutional Neural Networks. The goal of my research is to predict whether the shown stimulus during the encoding phase of a declarative memory task is going to be successfully recorded or not when tested during the encoding phase. This represents a challenge since the prediction uses different information from different tasks. If a certain stimulus is delivered when the likely to be remembered brain state is present, then performance in a memory task can be improved. Many studies reported significant changes in frequency band as well in event-related potential. For example, increased activity in theta band during pre-stimulus when compared later remembered and forgotten items at medial temporal sites, and a decrease in power over alpha and low beta bands in EEG signals over ongoing stimulus was found. On the other hand, ERP analysis in memory tasks reported a difference between 400 and 800 milliseconds post-stimulus onset. Prediction of successfully memory encoding has been attempted before in multiple paradigms, such as episodic memory and working memory tasks. A high prediction accuracy was achieved using intracranial electrodes in a working memory task. However, due to its not feasibility in daily life application, in this research we will use EEG signals because it has a low cost and it's easy to use. We record brain activity from 7 subjects. All of them have previous English education. The experimental paradigm consists in 2 phases, encoding and decoding phase. Encoding and decoding phases were separated by arithmetical distraction times to avoid the rehearsal of previous presented works. During encoding tasks, participants are presented with 5 lists of 50 English words each. During decoding tasks, participants are presented with 400 words and they were asked to select a confidence scale from 1 to 4. EEG data was recorded from 62 electrodes attached to the scalp. A sampling rate of 1000 Hz and all impedance were set below 10 kiloohms prior to the measure of the signals. Data was epoch into pre-stimulus and ongoing stimulus. Later, data was downsampled to 250 Hz and bandpass filtered from 0.5 to 40 Hz. We propose a CNN to predict the successful memory effects. The input of the network was a matrix of time points per number of channels. A kernel was used to segment temporal signals, and dropout with a rate set to 0.25 was applied to the input of the convolutional layer. Additionally, batch normalization was used. Rectifier linear unit was used as an activation function, and conventional methods were also used to compare our results. For this, event-related potential and common spatial pattern were used as feature extraction method, and linear discriminant analysis, supported better machine, and random forest were used as classifier. Significant difference of our results were analyzed using non-parametric bootstrap analysis. ERP analysis show a difference between remember and forgotten trials over frontal electrodes, while CSP results demonstrate that channels that carry the most relevant features per class are located in temporal sites. We perform classification using CSP and different frequency bands. The results show that the accuracy varies depending on the frequency used. Finally, it can be shown that the CNN results outperform other methods. Statistical analysis show a significant difference for the obtained accuracy when using pre-stimulus and ongoing stimulus in comparing with other methods. Our results show that the highest accuracy was obtained when applying CNN. For pre-stimulus, the accuracy was 71.6%, and for ongoing stimulus, the accuracy was 70.5%. CNN can not only extract temporal but also spatial features, which can increase the classification accuracy. Previous studies have reported difference in frequency band signals associated with different brain regions for later remembered items. Classification accuracy were not relevant for different frequency bands. And additionally, spatial analysis showed the relevance of frontal and temporal areas. These results could be applied to improve in-memory performance, which until now has only been intended but modulated neural oscillation using transcranial direct current stimulation, transcranial magnetic stimulation, or neurofeedback. Able to predict when a stimulus is more likely to be remembered, then we can control when the stimulus is given to the patient. Therefore, performance in a memory task could be increased. Thanks for listening. If you have any questions, you can contact me via mail. Thanks again.
I would like to thank the ICPRAI 2020 conference for giving me this opportunity to present a report. I feel very honored. I'm Haiyu Tang. I'm the author of Security Data Transmission of Smart Home Networks based on information hiding. This report is divided into 5 parts. First of all, an abstract. As we know, smart home can enable people to master the condition of their smart home remotely. However, privacy leaking in smart home network is neglected. Considering the privacy leaking in the smart home network system, this paper proposed a screen combining encryption and information hiding to ensure the security of data transmission. In the past few years, the widely used privacy protection screen set based on the idea of intermediate agent and cryptography. The cipher task obtained is usually in the form of garbled code, which is easy to attract the attention of attackers who attempt to decrypt it. Information hiding technology can conceal the secret information by turning unreadable information into invisible information. There are two innovations. Firstly, it can avoid exposing the sensitive data to the Internet directly and realize the protection of privacy. Data in question and information hiding are combined to realize the double protection of data privacy in smart home. This paper used DES equation algorithm to increase the smart home privacy information, after which the LSB information hiding algorithm is used to hide the cipher text. DES algorithm is a grouping equation algorithm which is composed of date equation and subkey generation. The equation process is shown as the picture. The scheme can achieve the purpose of information hiding by replacing the image LSB space with discrete information bits, so as Figure 3. Results. Before sending the discrete information is equated by DES equation algorithm, the result is shown as Figure 4. After that, the cipher text is hid into the cover image, shown as Figure 5. After the operation of information hiding, the sticker image is not different from the cover image, so the adversary will not notice the acquisition of sensitive information. Based on the discrete analysis of above two algorithms, the security stage has the trinity of high concealment, high difficulty in cracking. This paper processes a screen combining information hiding with equation algorithm. In the screen, the sensitive data are encrypted at the first, and then the cipher text is embedded into LSB of the cover image. After the sensitive information is embedded, the sticker image is the same as the cover image, so the adversary cannot easily find out the existence of sensitive information. The feasibility and security of the scheme have been verified by the simulation experiment and the security analysis. Comparing to the method of using equation algorithm memory, the scheme can do a better performance in privacy protection, making it more suitable for the smart home network. Part of our future is to propose more skilled equation algorithms, but also to ensure that they don't cost too much computation. In terms of information hiding, coverless information hiding technology is adopted, improving the concealment of secret information transmission by not modifying the cover image. My report is over. Thank you.
Hello everyone, my name is Menatallh. I'm from Zhang University. The title of my paper is Overview Research Progress on Pest and Disease Identification. In recent years, the identification of pests and diseases has become a hot topic. More and more researchers are dedicated to the detection and identification of pests and diseases to achieve precision agriculture.
Automatic detection of the number of pests on crops in the area has become an important means to optimize agricultural resources. With the development of modern digital technology, image processing technology has also developed rapidly, opening a new way for the identification of harmful organisms. During the agricultural planting process, timely and accurately analyze crop pests and diseases in order to make quick and accurate responses. Spray pesticides accurately on the affected area ensure the efficient use of pesticides and achieve high yields. This article will introduce the research progress of pest identification in the second part, including disease and pest identification, pest quantity and location detection, and the existing datasets. In the third part, this article will introduce some of the methods used in previous articles, summarized in the first part. In the second part, I have drawn different content into tables for everyone to read. First, some papers on disease and pest identification. Then, some papers on disease and then some papers on pest number and position detection. At last, some papers on existing datasets. The third part is an introduction to some methods, such as Qian, SVM, and so on. In the conclusion, this paper finds that most scholars' research is based on smaller data sets, which contain few samples of pest species, and most of the pest images are obtained under controlled conditions. The requirements for pest and disease identification in the actual environment can be well met. The above will lead to the actual applicability of the model is not, and the lack of relevant research to identify pests and diseases, locate and count pests, and determine the extent of disease in the meantime, so as to achieve precision agriculture. That's all. Thank you for listening.
Hello everyone. The topic of my speech below is related to crowd counting. However, due to the time limit, I'm afraid that many technical words cannot be explained in detail. If you are interested, you can email me later. My speech mainly starts from the three parts. The first part is the introduction. I will briefly introduce the importance and current situation of crowd counting. In the second part, I will briefly introduce several current advanced and effective crowd density counting models. However, due to the time constraint, I may only briefly introduce some of the innovation of this model and compare the pros and cons of each model. The third part is the summary part. I will briefly summarize each model and provide a way to think about where to try next. Recently, counting the number of people for crossing is a hot topic because of its widespread application, such as video surveillance, public security. The STEM incident frequently occur in large-scale activity at home and abroad, which has caused a lot of casualties. Therefore, the research on the population counting problem is getting hotter and hotter. Counting or estimate crowd size, both previous and in real time, is an essential element for planning and maintaining crowd safety in place of public assembly. Earlier research focused on estimating the number of people by detecting the body or head, while other methods run the mapping from the local or global feature to actual quantities. Recently, the population count problem was formulated as a regression of the population density map, and then the number of people in the image was obtained by summing the value of the density map. This approach can handle serious occlusion in dense crowd image. With the success of the deep learning techniques, researchers used CNN to generate accurate population density map and achieve better performance than traditional methods. However, population counting is still a challenging task due to large-scale variations such as several occlusion, background noise, and perspective distortion. Among them, scale change is the most important issue. To better handle scale change, the researcher had proposed many multi-column or multi-branch networks. This architecture typically consists of several columns of CNN or several branches at different stages of the background network. This column of branch has different receptive phase to seeing change in population size. Although this method has been greatly improved, the scale diversity they capture is limited by the number of column or branch. Here, I will show you some advanced CNN about crowd counting, such as CrowdNet, MCNN, CPCNN, CSRNet, DSNet, and if you are interested about it, you can find their paper to read. Finally, I believe that whether it is extracting multi-scale feature or gradually refining the density map, the most difficult problem at present is still how to make the model learn more distinguished features in crowd-intense areas, such as human head overlap and so on. And how can the model see the local feature of smaller scales in a wide-ranging image of the population density? That's all. Thank you.
Hi everyone, my name is Hong Lin and I come from Sun Yat-sen University, China. Today I'm gonna give you guys a poster presentation of my research. It is a review of application of deep learning in handwritten mathematical expression recognition. Here is the general content of my presentation. At first, I will give you a brief introduction to the research status of handwritten mathematical expression. As we all know, handwritten mathematical expression is a research highlight in pattern recognition area since it has many practical application scenarios, such as scientific document digitalization and online education. However, it can be very challenging due to its complicated two-dimensional structure. A great variety among different individuals. In our research, HME can be divided into two major parts, online and offline, based on the forms of HME. The former are received from small electronic devices such as pen-based tablets, while the latter are acquired from paper documents, as to say, offline mathematical expression of some images in most scenarios. Typically, we use different math models to deal with these two forms of data, but sometimes both of them can be presented as indistinguishable independent variable of one model that helps us predict the final outputs. Traditional process of HMER consists of two major stages, symbol recognition and structure analysis, which are described in detail in our paper. In the review, we can see many papers focus on improving one or more than one aspect in above two stages. However, some researchers have presented HMER system with global strategy that allow segmenting mathematical expression, recognizing mathematical symbols, and 2D structures of mathematical expressions simultaneously. We can call them global research. On the contrary, those approaches with two steps that I mentioned above are sequential approaches. Compared with the sequential approach, the global approaches can reduce our error propagation but require more computation resources. As we all know, deep learning methods are one of the top research highlights in recent years since they have achieved great performance in many specific application scenarios of science and engineering. Researchers begin to make use of those methods to solve the problems of handwritten mathematical expression recognition. To the best of our knowledge, by now there hasn't been a survey paper which provides an overall review about this promoting HMER methods published since 2000. And not a paper gives a detailed comparison between these two methods, including deep learning. In this paper, we will remedy this missing part by reviewing those important systems applied to HMER. In particular, we will pay more attention to those methods based on deep learning and emphasize their power and differences from other kinds of methods. In the third session of our paper, we firstly give a brief introduction of those commonly used deep learning frameworks. Then we introduce several end-to-end approaches that solve HMER problems to you. What's more, chain structured bidirectional LSTM to tree structural topology will be discussed in the paper. In the future, it should be a hot trend to combine statistical learning models such as HNN, CRF, and deep network. At the same time, new attention mechanism models such as transformers should be studied, since there hasn't been a research paper that focuses on the transformer structure which combine the HMER system. Finally, I hope that my presentation today will help you get a general idea of our work. Thanks for your time.
Hello, my name is Feng Zhang. I am honored to show my poster presentation at this conference. Today, I would like to present my paper, Application of Deep Learning for Online Handwritten Mathematical Expression Recognition, a review. There are 3 parts in my presentation. Mathematical expressions play an important role in describing problems and theories in math, physics, and many other fields, and it is an important field in pattern recognition. Based on the data collection mode, handwritten mathematical expression recognition can be divided into 2 recognition systems, offline and online. This paper focuses on online handwritten mathematical expression recognition, OHMER. OHMER still consists of 2 major problems. symbol recognition, and structural analysis. Symbol recognition can be solved sequentially and structural analysis globally. It was still around then, and etc. built a CNN for mathematical symbol recognition, and the structure is shown in Figure 1, and it is classic. Their model achieved 87% accuracy. Qian and etc. use a SSD model shown in Figure 2 for symbol recognition and Draculate for structural analysis to generate latex string. They use MAP score to evaluate their model, and it gets 0.65 in the best model. For OHMER, the input is a sequential data which makes RNN a more effective method. The best VLSTM proposed by Tang, Yuan, and etc. gets an accuracy of 87.7% on testing set test Chrome 2014. In addition, Zhang and etc. proposed a merged multiple 1D interpretations with advanced RNN VLSTM for OHMER. But the experiment shows that at the global expression level, the recognition rate with no error is low, which is only 13%. In 2017, Zhang, and etc. proposed GRU-RNN, in which the input two-dimensional ink trajectory information of handwritten expression is encoded to high-level representations via the stack of bidirectional GRU-RNN, and the decoder is implemented by a unidirectional GRU-RNN with a coverage-based attention model. The experiment shows that the accuracy of recognition is 52.43% in competition dataset Chrome 2014. Even though the accuracy of recognition is not satisfactory enough, this research proposed a model that is capable of performing symbol segmentation automatically and learning to grasp a math grammar without prior knowledge. Draculate and Misaki Nakagawa present an advanced end-to-end system employing CNN based on the attention-based encoder-decoder model. In 2018, Zhang and etc. proposed a novel end-to-end based approach named Check, Attend, and Pass (TAP), consisting of a checker and a passer equipped with a guided hybrid attention. The TAP model achieves a recognition accuracy of 61% on Chrome 2014 and 57% on Chrome 2016, outperforming the state-of-art methods published by Chrome competition, which makes an improvement on OHMER. Both offline and online handwritten mathematical expression recognition have got improvement with the application of deep learning. However, there are still many problems to be solved, and the major problem is that existing work on OHMER can only achieve high recognition accuracy on handwritten mathematical symbol recognition. On long handwritten mathematical expression with complex structure, there is still a lot of room for improvement. Most of the proposed model can only achieve recognition accuracy of about 50 to 60% on standard competition dataset, which is far away being applied on realistic tasks. This paper is aimed at bringing new information and ideas to researchers and jointly promote the further development of OHMER. Thank you for watching.
Hello, I am glad here to share our paper, Comparison of Persian Handwritten Digit Recognition in Three-Color Modality using Deep Neural Network. As you know, color is a key feature in human visual system. Similarly, in most computer vision applications, color is a discriminative and important feature. So the effect of color as a feature has been studied in many computer vision applications. But to the best of our knowledge, so far no one has investigated the effect of color in a handwritten recognition. So this paper for first time tried to see whether color modality of handwritten text, especially Persian isolated digits, affect their recognition, accuracy, or speed. To design system, the three similar convolutional neural network in bracket CNN model are designed for recognizing Persian isolated handwritten in three-color modality. This architecture shown in this figure. As shown in this figure, there are two convolutional layer, two max pooling layer, and two fully connected layer in proposed CNN models. Also, as shown in this table, there are plentiful parameters that should be trained in training phase. For training CNN models in three-color modality, a subset including 13,330 samples of Persian isolated digits which have three-color modality are selected. And then this selected data are divided into training, validating, and testing set. One example of three image color modality in digits are shown in this figure. As shown in previous slide, proposed CNN have a plentiful parameters that should be optimized in training phase. For training this huge number of parameters, there must be enough image samples. In this paper, we applied simple geometrical transformation like shifting and rotation are applied on input image and create appropriate image for training proposed model. After training our models, overall recognition accuracy for each digit class in three different image modality are shown in this figure. As seen in this figure, black and white modality has a higher performance compared to other color modality, but these differences are not significant or meaningful. In terms of network convergence, black and white is faster than two other color modality, and this inference are shown in this figure. Also, in terms of training and testing time, black and white modality is much better than two other color modality. As a conclusion and future work, in this paper we investigate to see whether color modality of handwritten digit, Persian handwritten digit affect their recognition accuracy and training time. Sample of Persian isolated digits which have three color modality are selected and divided into training, validating, and testing set. Similar CNN models are created and designed and then trained with our sample. The experimental result on a training set show that CNN on a black and white image has a higher performance compared to two other color modality. Also, comparison of training time in three color modality show that recognition of handwritten digit, Persian handwritten digit in black and white is much more efficient. In the next study and as a future work, we want to investigate the same question in word and text in different script.
Hello everyone. In this video, I am going to give a quick overview of our paper called Unlacement and Interlacement Shape Descriptors. I am Michael Clément from the University of Bordeaux, and this is a joint work with Camille Kurtz and Laurent Wendling from the University of Paris. In this paper, we propose a new method to describe 2D shapes. For this, we employ a model called Unlacement. This model was initially proposed to describe the relative position of two objects, when they are in complex spatial configurations. For example here, an object A is partially surrounded by another object B. This situation we call unlacement. The two objects can also be intertwined together, and we call this interlacement. The model for this descriptor is directional. It is a feature vector where each value corresponds to the unlacement quantity in a given direction theta. The descriptor is usually computed over an interval with a finite number of directions. If you are familiar with the radon transform, the computation scheme is a bit similar. We integrate a function over all the lines that traverse the objects in a given direction theta. For the function on a line, here we multiply and cumulate the length of the segments, which are in alternating patterns, A, B, A. In this way, we quantify how much B is unlaced by A. It turns out that this model can also be applied directly on a single 2D shape. Here, we consider the shape as one object A, and for the object B, or A bar, we consider the complementary surrounding disk. By doing so, the shape is described in terms of its directional concavities. For example, if the shape has deep concavity patterns, like stripes or S-shapes, in a direction, then the value for the descriptor in this direction will be large. On the contrary, if the shape is convex, like a circle, the value will be close to 0. Different versions of this descriptor can be used, depending on if you consider the unlacement of A with regards to A bar, the opposite, A bar with regards to A, or the combination of both, which is the interlacement. In the paper, we discuss the geometrical properties of these descriptors. They are symmetric, equivariant to rotations, and invariant to translations and scalings. For the experimental part, we applied the descriptors for 2D shape recognition task. The Charvit dataset here is composed of two parts, B1 with 100 shapes and B2 with 200 shapes. Here we use KNN classifiers and a leave one out cross-validation strategy. We report the accuracy obtained for different baseline shape descriptors, such as the thermic moments or the generic Fourier descriptors. Here we compare to our proposed descriptors. We have the unlacement A with regards to A bar, the opposite A bar with A, and the interlacement I. We also have the different combinations of these descriptors. We can see that the combinations tend to improve the accuracy result, showing that each version of our descriptors contain discriminative information for shape classification. For this dataset, the best results are achieved by global descriptors such as GFD, but we will see next that with more complex shapes, the unlacement becomes more powerful. So next we use the CVC dataset. It has 3,000 technical drawings, and here we use KNN as well as support vector machines with linear and Gaussian kernels. In this table, we report the accuracy for the baseline GFD and for our proposed descriptors. On this more complex dataset, the unlacement and interlacement shape descriptors perform better for all tested classifiers. This shows the interest of using our proposed model. In future works, we plan to extend this approach by considering the topological skeleton as well as the spacing between the concavities. The model will also be applied to more complex recognition tasks. Thank you for your attention, and if you have any question, you can contact me by email. I hope you enjoy the rest of the conference. Goodbye.
Hello everybody, this is Ghazal Hafsai. I have the pleasure to present you our research entitled An Integrated Deep Architecture for Lesion Detection in Breast MRI in a poster session for ICPRAI 2020. Breast cancer is the most common cancer in women worldwide. Early diagnosis of breast abnormalities is proven to play a decisive role in survival rate. Computer-aided detection can be advantageously used to help physicians in tedious task of abnormality detection in breast images, and in the case of this research, magnetic resonance images of breast. Recent advancements in deep learning-based architectures have made a great stride in biomedical image processing. When a deep neural net is properly trained, it can capture the nonlinear nature of the data, so they can extract key features and subtle structures of medical images, which are not even visible to human eyes. A number of deep learning-based object detectors are nowadays available that can be adapted and tuned to work as an abnormality detector. In this research, we propose integrated strategies to achieve the best possible performance, both in terms of precision and reduction of missed rate. Faster RCNN, YOLO, and GradCam are the three implemented methods from the literature. The working principle, associated parameter, and setup for each method is discussed in the paper. All three methods are trained using three different architectures in backbone, including ResNet-50, MobileNet version 2, and GoogleNet. The setup with the highest achieved performance of each object detector is used for developing the integrated method. This slide contains the pseudocode for the integrated approach. For each test sample, the bounding boxes by faster RCNN and YOLO are firstly computed. The overlapping ratio between all detected bounding boxes is then obtained. If the overlapping ratio is more than 50%, the two detections are considered to refer to identical abnormalities, and in that case, a linear regression model is used to determine the final bounding box of such abnormality. If the overlapping ratio is less than 50%, the integrated solution takes in both detections as a positive case. Finally, the detected bounding boxes are compared with the boxes achieved by GradCam method, and the overlapping ratios are computed. Again, if the overlapping ratio between the detection by GradCam and YOLO or faster RCNN is less than 50%, the GradCam detection is added as a new detection. Well, 5 other integration strategies are also implemented. Firstly, the union of faster RCNN and YOLO that excludes the GradCam detection from the previously discussed integration. Secondly, the intersection of faster RCNN and YOLO, which only includes linear regression output of the match detection between the two object detectors. The faster RCNN priority that includes linear regression output of match detection by faster RCNN, which are not detected by YOLO, and similarly YOLO priority that includes linear regression output of match detection between faster RCNN and YOLO, as well as detections by YOLO which are not detected by faster RCNN. And finally, the intersection of faster RCNN and YOLO plus GradCam, which includes linear regression output of match detections between the two object detectors and also detections achieved by GradCam. So if there is any disagreement between YOLO and faster RCNN, the detection is simply dropped. Details about the database that we have used in this work, as well as all the experiment setups, can be found in the paper. These are the precision recall curves for the methods from the literature with different backbone architectures as well as different integration approach. As you can see, the intersection of faster RCNN as YOLO is giving the highest performance. This slide illustrates miss rate against false positive per image. As you can see, the minimum miss rate can be achieved by the integration of all methods. The following slides visualize some of the detection results on our database. And thank you for your attention.
Hello everyone, welcome to my presentation. Today, my topic is image orientation detection using convolutional neural network. My name is Zhang. I come from East China Normal University. This research comes from the requirements of real applications. For example, smartphone management. With the popularity of digital cameras and smartphones, we can take pictures anywhere and anytime. I think everyone have encountered this situation. In order to take better photos, we always adjust the camera or smartphone. But this brings a problem, that is, after taking photos, the direction of the photos in the album is sometimes reversed, which makes it inconvenient for us to view the photos. Although some devices will automatically adjust the photo direction according to the gyroscope, not all devices have this equipment. On the other hand, the accuracy is not always very high. Another application is the mail sorting machine. Now we use 6 red squares on the upper and left corner to detect the orientation. But if we can use the image orientation, it will be more convenient and economically. The network used in our experiments is designed with 2 principles. First, we think image orientation detection is not a complex task, so we do not need to apply a very deep convolutional neural networks. In practice, we use 4 convolutional layers and 2 fully connected layers to build the network. Furthermore, the main purpose of this network is to detect orientation. So we think the ordinary square kernels of convolutional layers is not suitable or enough for this task. So in practice, in our network, we add 2 more kernel size of convolutional layers, 1 plus 3 and 3 plus 1, to exact features with more direction information. 6 datasets are used in our experiments. The first one, LFW. This is a face recognition dataset. The second to the fourth datasets are collected from the internet by searching with keywords block, indoor, and landscape. The mail dataset is collected from real mail sorting machines, so there are only 2 directions in this dataset. The last one is ImageNet 2012. We compared our model with AlexNet, GoogleNet, and VGGNet. The results indicate our method is more suitable for image orientation detection task. We obtain better performance than other networks. This is the confusion matrix. We can find that the recognition rate is highest when the image correction is correct, as the 0 degree. In addition, on the ImageNet 2012, the recognition rate after rotation has dropped more significantly. The reason of this phenomenon may be the images in ImageNet are more complex. Thank you for your participating. Thank you.
Hi, I am Viviana Beltran. I am from University of La Rochelle, and I will present our work titled Evaluation of the Impact of Different Models in the Syntax Visual Question Answering System. I work in collaboration with Michael Costati, Nicolas Journet, Juan Caicedo, and Antoine Dosset. The main goal of our paper was to study the relevance of different components contained in a traditional BQA system that are focused on solving the task of syntax recognition. The first model we studied was the model A, which is in charge of computing features from the different modalities included, in our case, visual and textual modality. The model B is in charge of using this information coming from these modalities, as well as applying the attention mechanisms that we explore. The component C is in charge of handling the answers. It could be a fixed space or it could be a dynamic space, and that's why we included the model C, which is called the model D, which is called copy model, and it's one of the most important ones, and the model E, which is in charge of including complementary data. The copy model is in charge of adding a set of dynamic spaces. These dynamic spaces are in charge of including new information, new tokens that are not included in this fixed space, because as we see, the set of different combinations of characters that we can find in natural images could be limited. Therefore, we definitely need a way to include this new information, and this is what the copy model does. If we see this example, each one of the images can have associated different questions, and each one of these different questions is aiming to targeting different textual data contained in the image. We can have a score that is assigned to each one of these tokens, and it depends on the quality, first in the quality of the OCR system used to extract these tokens, as well as the correctness of the questions made, because sometimes the questions, the information that the question is required is not really contained as a textual information in the image. Therefore, the quality of the database is also important. And we can do a perfect match and a partial match. If we do a perfect match, we may have a scores of 0 for all the tokens, because probably all of these tokens are separated. In the case of answer that contains more than 2 tokens, then there is not going to be a perfect match. In the second question, this is possible because the answer is only composed of 1 token, and then if the OCR system really recognizes the whole word 1, then we can have an assignation of a score of 1. If no, a partial match is the best option, because we can assign a score based on a level change distance that is going to compute a better match between each one of the tokens and the ground truth answer. Here we have the results. We explore different features for each one of the modalities and determine which one was better. In our case, for the visual data, it was better when we included some kind of attention in the extraction of the visual features. We also explore the size of this additional space, how many new spaces we can include, and of course, if we include more spaces, the performance is going to improve, as well as what is the best complementary data that we can include by using this subnetwork. In our case, by using OCR fast text features. And this task we see is very challenging, because here we're having accuracy of 25%, while in traditional BQA system this accuracy reaches almost 80%. So this task is very challenging because the system really needs to do a reasoning between the textual and visual information. One of the main conclusions here is that although in our case, by the inclusion of OCR, of a copy module that uses the OCRs that we can extract from the image, we can improve the performance. This also is adding a set of randomness, a feature of randomness to the training, because for each image, these spaces are changing. So that is the main conclusion of our work. Thank you very much.
Hello everyone, my name is Hongchen from China Zhiliang University. I'm glad to present my work, Multi-Layer Cross-Domain Non-Negative Matrix Factorization for Cross-Scene Dimension Reduction on Hyperspectral Images. namely MLCD NMF. This work combines the idea of dictionary non-negative matrix factorization and a stacked autoencoder. It has 4 characters. First, it provides the ability of both homogeneous transfer learning and heterogeneous transfer learning. Second, it contains 2D NMF layers and works in a way like SAE. Third, it is beyond SAE due to the graphs built based on correlations between samples. Fourth, it is a flexible model which does not require strict one-to-one sample correspondences between different things. Then let me introduce it in detail. MLCD NMF has 2 autoencoder layers implemented by DDNMF. The first layer is used to align different input feature dimensions to a same one, and the second layer further enhances feature invariance between source and tagged things. We can see from Figure 1. It shows the process of NMF is exactly a non-negative autoencoder, so we use NMF to build an autoencoder. In MLCD NMF, in order to maintain within-scene and cross-scene data manifold structures, we build 3 graphs, namely source-to-source graph, tag-to-tagged graph, and source-to-tagged graph. In within-scene graphs, we use dot product weight. As for cross-scene graph, we use 0-1 weight. In MLCD NMF, the cost function is defined as equation 5. And we can see from Figure 2, it is the framework of MLCD NMF. We can see that this model is built by stacking DDNMF layers in the way of SAE and adding the activation between adjacent layers. In order to test the feature invariance, we did the following steps. First, train the dimension reduction model with both source and tag training samples. Second, perform dimension reduction on source training set and tag test set in order to obtain low-dimensional features. Third, train a spot vector machine classifier on source training set. Fourth, perform the prediction on tag test set and evaluate their accuracies. Then we can see from Table 1. It shows accuracies achieved by different dimension reduction algorithms. It implies that the proposed MLCD NMF achieves better accuracies among all compared cross-domain dimension reduction algorithms, namely MA and DDNMF. In conclusion, this work has 2 DDNMF layers. Those 2 layers are stacked to form a crossing SAE, and it conveys more crossing feature invariance than DDNMF. Moreover, MLCD NMF provides the opportunity of nonlinear feature extraction through the activation between layers. Experiments show experiments on a crossing hyperspectral image dataset have confirmed the superiority of MLCD NMF. That's all. Thank you.
Hi everyone, I'm Yonggang Li from Peking University, China. It's my great honor to share our work here about the differentiable architecture search. Neural architecture design is a crucial step for neural network-based methods, and it requires years of experience and extensive work. In recent years, neural architecture search has automated the process of architecture design. In particular, differentiable architecture search abbreviates thus reduce time cost of neural architecture search to a couple of GPU days. Thus break down the network search problem to the search of cells, and seek self-found cell to build a network. Every cell in DAS is directly on cyclic graph nodes. Figure 1a shows a cell with 4 nodes, and they selected for operation between every possible pair of nodes. To make the search space continuous, just relax the category choice of a particular operation as a softmax of all possible operations, as shown in the second equation. With this relation, just search the parameters alpha with a bilevel objective, shown in the second equation. Although DAS achieve great performance in image classification tasks, there exists a large architecture gap between the search stage and the evaluation stage of DAS. In the search stage of DAS, there exists a mixed operation with 8 candidate operations in every connection of the diagonals, whereas in the evaluation stage, DAS only resolves operation with highest probability in each connection of the final architecture, and retrain the final architecture to get the final performance. Consequently, the architecture found by the search stage of DAS cannot guarantee the best performance in the evaluation stage. To narrow the aforementioned gap between the search stage and the evaluation, we propose an algorithm to progressively eliminate some candidate operation in the edges. As shown in those 2 equations, we propose 2 strategies to reduce the ball gap. For strategy 1, we greatly fix the operation with highest confidence, which means that every step will close the gap of one edge. For strategy 2, we remove the operation with the lowest probability among all remaining operations, which will close the gap in a more fine-grained way. With those 2 strategies, the pipeline of our method can be shown as figure 1. Firstly, we randomly initialize the architecture as in DAS, which ensure all candidate operation has nearly equal probability. Secondly, we utilize the first-order search algorithm of DAS to search the epoch. Thirdly, we mask the architecture by stage 1 or stage 2 and continue search as epoch. This procedure is repeated and until the operation in each connection is damaged. Finally, we get the final architecture from the above procedure directly. We evaluate our methods on both CENPARMI and CENPAR100 datasets. As shown in Table 1, Strategy 2 achieved better results compared with Strategy 1, although the mean performance of Strategy 1 is better than Strategy 2 in CENPAR100 datasets. The architecture found by Strategy 2 is more stable than Strategy 1. Furthermore, the proposed PDDAS achieve comparable results as opposed to PDAS and PCDAS, and surpass DAS by larger margin. Compared with PDAS and PCDAS, the architecture found by our methods obtain better performance, and the plan scalar is better than architecture found by those methods. Moreover, our methods have lower search cost, less than 0.5 GPU days. For more details, please refer to our paper and feel free to contact us. Thanks.
Hello everyone, it's my pleasure to make an oral presentation at ICPRAI 2020. The title of my report is Transformed Network Based on Task Driving. I am the reporter Zhou, and my supervisor is Li Hongjun. I divide my report into 4 parts. Number 1, motivation. Conventionally, we design a network structure according to a specific task and then update the parameters, or we directly apply the part of the existing network structure into a new task according to the idea of transfer learning, and then fine-tune the parameters. However, based on the question of is this network structure the most suitable for the task, we propose a novel idea and affirm that the network structure can be updated like the network parameters. Number 2, methodology. We propose 3 types of update manners to address that question. the vertical update, horizontal update, and the cross update, in which the cross update is the selective use of the vertical update and the horizontal update, as shown in the figure of 2. The conventional backpropagation mechanism does not match the unfixed network structure, so we propose a multi-branch arrow backpropagation. And the advantage of which is that it ensures the performance of network can obtained by each update is optimal. We combined with the recognition task and propose 2 objective indexes, that AC and ETS. They are respectively refers to the growth rate of accuracy and the growth rate of time consumption for training. And figure 4 refers to the relationship between the update and the accuracy with the time consumption. Number 3, simulation. We also conduct some experiments on one dimension and 2-dimension dataset about recognition, and the datasets and the details of datasets and the parameter settings of each dataset are respectively shown in Table 1 and Table 2. Figure 5 is the experimental results on various datasets. Number 4, summary. Contributions. First, the idea of updating the network structure like the network parameters is proposed. Number 2, a multi-branch arrow backpropagation is designed to match the unfixed network structure. Number 3, some contributions evaluations are proposed. Future work. We will explore more manners to update network structures. Second, we will propose appropriate contribution evaluation indexes according to different specific tasks. Last but not least, we want to design a highly integrated platform to be flexible and generalizable to multiple taxes. That's all my report. Thanks.
Topic is a blockchain-based online game design architecture for performance issues. I will start from introduction and blockchain performance issues, then blockchain online games design strategy, lastly conclusion. Blockchain technology was first proposed by Satoshi Nakamoto. It's a decentralized, non-temporable, traceable, and trusted distributed database that is jointly maintained by multi-participants who do not trust each other. This is a data structure of Bitcoin network. Each transaction will be consistently recorded in the nodes of the entire network after it's verified and agreed by the majority of participants on the entire network. With the rapid development and widespread application of blockchain technology, blockchain games have begun to appear. Blockchain is suitable for applying in games, but there are rarely good games. This diagram shows that the trend in activity of top 10 blockchain games. The reason for the large changes in activity is blockchain performance issues. TPS is an important indicator used to measure the performance of the blockchain. According to Satoshi Nakamoto, the TPS is proportional to the block size and the growth rate of the main chain, inversely proportional to the byte size of each transaction. Let's talk about the V, the growth rate of the main chain. When fork happens, we can get this equation by accumulating the probability of a certain situation and the value in that situation. And if we assume that the transmission time range of blocks in the P2P network is from 0 to 2A and is evenly distributed, then we can get this equation. Let's make a graph we can see in the real production environment because the fork of the blockchain is inevitable, and the line chart proves that it's difficult to significantly improve the performance through the blockchain generation rate when the size of the block and each transaction date are unchanged. We proposed a design strategy suitable for blockchain games with the same response speed as traditional online game, and taking advantage of blockchain technology in game scenarios. We consider using a blockchain network in a game application with a traditional server instead of just using a blockchain network to complete all network requests. For the network request to propose through the blockchain network, we design a cache system to improve the processing efficiency of the system. The data request is first retrieved in the Redis cache, and if the query key is hit and the value is correct, the key value pair is directly manipulated and returned, then synchronized to each blockchain network node. If the record is not hit, the data operations will be added to a message queue waiting on the blockchain network. This is the data structure in Redis. It's a nested dictionary. Lastly, we supplement some test results. We use this test script to make 10 times requests and the result below. That's all. Thanks.
Hello everybody, my name is Phoebe Chan and I will be presenting the poster named A Comprehensive Unconstrained License Plate Database on behalf of my co-authors, Nicola Nobili and Malaya Bloom from CENPARMI at Concordia University in Montreal. CENPARMI is currently building a large database of license plates from several countries, since databases that we found only contain plates that are limited to only one region, have few points of view, and were taken in ideal environments. Our goal is to create a more challenging database that included license plates from many countries, states, and provinces, were taken from many different angles and heights, has moving and stationary vehicles, and offers some challenging environment conditions such as snow and rain. AAMVA stands for American Association of Motor Vehicle Administrators, and we have included their proposed guidelines for license plate as reference on the poster. Due to time constraints, we will not be discussing the images of samples of challenging license plates and database photo variations, but feel free to look at them at the end of this presentation. Without further ado, here are the contents of the CENPARMI license plate database. We have plates that are 1. Clean, legible, and taken at a close distance. 2. From a long distance. 3. While cars are moving. 4. Various angles. 5. While walking. 6. Under challenging weather conditions such as rain, slush, and snow. 7. Broken, bent, rusted. 8. Colorful backgrounds. 9. Have stickers or other markings. 10. Difficult fonts. 11. Varied font colors. 12. Plates composition. 13. Protected by tinted or smoke cover. 14. Have license plate frames from dealership or other organizations. Camera used for this project include Canon, Apple, Sony, LG, Samsung, and Vivo. The CENPARMI license plate database currently has 2,200 images, and locations range from Japan, Canada, US, Jordan, Palestine, and Turkey. In conclusion, we are still in early stage of collecting license plate images and intend to increase the number of samples through the variety of images by using different capture devices and lenses. As for future work, we manually extracted some isolated characters from a few selected license plates. Yet this process will be time-consuming with the increase in samples, so we are working on building a semi-automatic tool to assist in this labeling procedure. The software will locate the license plates within an image, perform OCR on the plate, and attempt to identify it and extract the isolated characters from them. The user will have the ability to change the automatic proposed labels. Information we intend to include for each image will include the captured device, camera brand and model, resolution, lens, focal length, number of license plate in the image, the location of the plates within the image, the content of the plates including any special symbol, and the country the plate was issued. Temporal information such as time of day and season, and physical information such as plate occlusion and the weather situation such as rain, snow, mist, or fog that can affect recognition will be included as well. Some photos were taken through a window, and in some cases either the vehicle, the camera, or both were in motion. Thank you for attending our presentation. We hope you enjoy it. Bye.
Hello. I'd like to briefly summarize for you our paper entitled Advanced Data Pre-Processing for Detecting Cybercrime and Text-Based Online Interactions. Our motivation for doing this research is to ultimately help law enforcement find and prosecute child sex predators. One of the mediums sexual predators use to lure their victims is via online chats. The problem with online chats is that they are supported by many different software vendors on all sorts of diverse platforms. For law enforcement, getting the data is a challenge, but then sifting through it to build a case is another challenge. This, added to the fact that law enforcement has limited resources, makes it clear that if you're going to make the internet a safer place for children, then law enforcement needs help. There are basically two phases law enforcement needs to go through in building a case against the suspect. First is document acquisition, and the second is document management and analysis. Our focus is aimed at document management and analysis. Basically, we'd like to put together a comprehensive solution for law enforcement that, 1, allows them to manage the large amounts of documents related to a particular case, and secondly, provide tools that can analyze those documents, looking specifically for incriminating documents that can be used in a court of law. But before any analysis can be done on documents, specifically chats, we need to convert these chats into a standardized format. We refer to the standardization process as chat normalization and is the main topic of this paper. Once converted into text, there are basically two types of chats you have to deal with: structured and unstructured chats. Structured chats are those that have metadata in them, for example, XML and HTML. Unstructured chats are those that only contain the contents of a chat, that is, no metadata. The difficulty with being able to automatically normalize a chat depends if it's structured or unstructured. With unstructured chats, it's possible to have a fully automated way of normalizing them. With structured chats, on the other hand, it's generally not feasible, and we generally choose to implement a semi-automatic method to normalize them. The paper defines semi-automatic normalization as requiring a user to specify a one-line description of the chat header format. We refer to this as the chat template. Normalization uses this template to parse out the chat header from the chat text. Automatic normalization defines a process where software is able to scan a chat and automatically build a chat template. In turn, the template is used to normalize the chat in the second phase. The end result is a fully automatic way of normalizing a chat. Chat normalization is an important process for anyone who needs to analyze chats or to use chats for machine learning. In this paper, we try to help in how to deal with them in an effective manner, especially in situations where you need to gather your own data for purposes of training or analysis. Hopefully, you find the information in this paper useful in this regard. Furthermore, as a possible point of discussion is a software we've built that manages chats, converts chats to text, normalizes them, consolidates them, that is, links chats by authors, anonymizes chats, which is useful for generating training data, and finally uses an AI engine to find suspect chats, all in one software we named Resolute. Again, thank you for your time and interest.
Hi everyone, and thank you so much for your interest in this paper. This is Ali Turani, the presenter of the paper, A Real-Time License Plate Detection Method Using a Deep Learning Approach. In this research, we have proposed a method to detect Iranian license plates in still images and video frames, which works as a representation of vehicle presence. Our method has the advantages of high accuracy and real-time performance due to utilizing U-only log once or YOLO version 3 as a robust deep learning approach. We have briefly introduced some of the most common types of deep neural network-based approaches for object detection purposes, including convolutional neural networks, RCNNs, fast and faster RCNNs, and different versions of YOLO to prove why we have utilized YOLO version 3. Well, the input of the system is a series of vehicle images, and the output is the processed image with added bounding boxes containing the vehicle's license plates. In this regard, a set of images is fed to YOLO version 3 to train the network and generate an LPD model. To achieve better training results in the model generation, the input images are pre-processed using low-pass filters like histogram equalization to remove any existing noises. This can be really helpful in some challenging scenarios like high illumination conditions. We have also described the configurations of the employed YOLO algorithm, like a reduction factor of 32, which is used to break the input image into equal grids, and the YOLO's number of detectable objects inside each grid, which is equal to 9 as default. In addition, we work on the correct tuning of anchor boxes to obtain great output results and modified these parameters based on dimensions of a standard Iranian license plate, which has the aspect ratio of 4.298 to 1. Other parameters, including the bounding boxes width, height, and vertical and horizontal locations of a box confidence score, which is also known as the objectness factor. Our system has been trained and tested on real condition data, that is, the images captured in real circumstances, including different resolution, weather, and illumination conditions. Since we could not find any standard Iranian license plate dataset available, we had to acquire real condition data and generate a dataset for train and test purposes. Accordingly, we installed a camera at the entrance of a parking lot and captured images of vehicles under the supervision of a surveyor. You can find the properties of the dataset in the paper. The dataset images are classified into front and rear view classes, each comprised of instances captured in both normal and challenging scenarios. Since the number of instances was not enough, and to enlarge the training samples and provide a wider range of data, we have utilized some common data augmentation techniques, including horizontal flipping. In this regard, the total number of data, I mean the sum of real and augmented data, became more than 21,000. Then we utilized a manual image annotation application for labeling data, which was a tough process, by the way. We used 75% of the data for training and the remaining 25% were used for evaluation. The proposed method resulted in more than 98% accuracy in the correct detection of Iranian cars' license plates. On the other hand, and to compare the effect of employing YOLO version 3, we have done the same experiment with YOLO version 1. Experimental results showed that YOLO version 3 could detect the vehicle's license plates in the range of 10 to 70 milliseconds, which is about 2.2 times faster than YOLO version 1. Finally, in terms of contribution, I can refer to the process of fine-tuning of YOLO version 3 algorithm to provide a high accuracy system for license plate detection, as well as a well-designed license plate detection system for real condition circumstances. We have generated a dataset of vehicles with Iranian license plates in various environmental conditions and applied data augmentation techniques to provide a wider range of data variety for good model training. Thank you so much for your time.
Hello everyone, this is Al-Qawasmeh, a PhD student working in handwriting analysis project. I hope you are all in a good health. One of my research topics is stress detection from handwriting, as stress is a growing problem in societies due to many stressors that we are exposed to in many aspects of our daily lives, such as work environment, social, academic, and emotional issues. It can also be considered as a reaction from our bodies and minds after physiological, psychological, and environmental change through our lives. We can notice symptoms of stress in many aspects of our lives, such as health, thoughts, feeling, and behavior. If early symptoms of stress are neglected, they will over time turn to chronic diseases such as high blood pressure, heart diseases, obesity, diabetes, and mental diseases like anxiety disorders and depressions. So being able to recognize common stress symptoms can help to manage them. Many studies have been done on stress detection. Since stress affects our life significantly, these studies can be grouped into four main aspects: psychological, physiological, behavioral, and physical. Handwriting is considered as a behavioral response. The most important advantage of behavioral responses is that they do not require a special equipment, which leads to reduce the system cost. Moreover, these methods are unobtrusive to the users. One of the biggest challenges in the handwriting analysis system is the lack of label databases to enable active innovation. Currently, as far as we know, there is no public label dataset for stress level detection applications. Also, the high similarity in handwriting between people is a big challenge in our work, so we will put a considerable effort to set the most discriminative stress-related features to get a high classification rate. In this study, we aim to provide a system that overcomes all these challenges and develop a powerful stress level detection system from handwriting. The manual stress detection process is expensive, tedious, and exhausting. This makes the automation of the detection system important. In our research, we will focus on automating the level of stress detection system from handwritten documents. Figure 1, as you can see, shows the general structure of our stress level detection system. In this research, we will present a novel database of English handwritten documents, each of which is annotated to detect the writer's level of stress. Also, we will work on a machine learning based detection system by extracting a set of features recommended by a psychologist together with a graphologist. These features will be fed into different classifiers to detect stress level. The performance of such systems should be evaluated using a large data set that includes hundreds of documents written by different writers. A new data set will be collected and labeled regarding stress level. The writers will be asked to fill up an information sheet that consists of a set of questions about age, gender, years of study, mother tongue, handedness, ease of writing, and the pleasure of writing. The writer will also be asked to fill up a perceived stress scale (PSS) questionnaire to determine their level of stress. In the feature extraction phase, the most relevant information is extracted from a raw data and represented in a reduced set of feature vectors. The performance of the classification system is highly dependent on the extracted features. So we will use some image processing techniques to extract the most relevant features to our problem. Here are some of the manual features that we will extract to detect the stress level of the writer. First, pen pressure, where heavy pressure related usually to stressed people. To extract this feature, we will use the standard deviation and the mean values. Second, handwriting slant, where stressed people usually have downward direction. To extract this feature, we will use least square method to find the least fit line of the foreground pixels. The last feature is handwriting irregularity, which is one of the most important features that reveal stress. We will measure lines irregularity using the vertical and horizontal projection profiles. The last phase of our system is the feature analysis. We will use SVM method for classification, as support vectors are used to find the maximum margin between the vectors of the two classes. And for non-linearly separable data, support vector machines give us the ability to map the feature space to a higher dimension where we can find a hyperplane that separates the features linearly using non-linear mapping. To sum up, the main points of my work are: first, a new dataset will be proposed and labeled regarding the stress level of the writer. Second, we are also proposing a machine learning based system to detect stress level from handwritten documents. And finally, we are proposing a new stress related features recommended by a psychologist together with a graphologist. Thank you very much.
Everyone, I'd like to present our research results for using social media and neural networks to predict US elections or elections in general. Let me go to the next slide. Sorry. Okay. So the motivation behind the research is that a lot of politicians and political parties are making heavy use of social media these days, in particular Twitter. So it's a good idea then to gauge the elections based on subscribers to each candidate in Twitter. We were able to collect, for the 2016 election, prior to election, 7.8 million subscriber profiles for the two candidates, which we're using in our model. And one major premise that we're making is that city names are related to the founders of the cities, and they're related to the language of those founders. So we could use that to predict city names by and their states that they belong to. And we've decided to use a CNN with GPU acceleration in order to determine the pattern of city names and states. And in order to encode it for the CNN neural network, we've decided to encode the city names into bigrams. That's so each city name is encoded with 2-letter bigrams. What you saw before was all the states in California encoded. And what you see here is one city in Florida being encoded. And this is a two-dimensional representation with the color intensity being the frequency of the bigram. We had over 695,000 cities that we input into the model, into the CNN model, and we did the typical 80-16 4% test split. We did some data augmentation. We built a CNN based on 5 2D convolutional layers using Keras and TensorFlow. Typical type of training hyperparameters, nothing unusual there. We did tenfold cross-validation in order to make sure we didn't have any data imbalance and the model was stable over the whole data set, as you can see with the variance being very low in the cross-validation. And we also did some model testing, figuring out the false positives and false negatives. And it's relatively low for the false positives and negatives. And we had an overall prediction rate of 84%, 84.43%, which is pretty good. Good enough to make predictions in the model, using the model on the US election. So as mentioned before, we're using the locations of each one of the subscribers to the 2 candidates. This one here, we counted the subscribers by state. And what you see is on the x-axis is the state name and the y-axis is the percentage win by that candidate by population. So as you can see, the predicted and the actual, the gold line tracks very well with the predicted values. Similar for the Clinton candidate, both predicted and actual are tracking well. And at the end, what we found was that we had an overall accuracy by state of 90%, being that 5 of the states that we predicted mismatched with the actual values. So that was quite good result. So you may notice that we had used a popular vote model instead of electoral vote model. What we've decided is that since the electoral voting system is based on who wins a popular vote in particular states, it was valid to use a popular vote instead of going to the complication of determining electoral votes. So we were successful. Our conclusion was to reframe a text classification problem into image classification problem using CNN and GPU acceleration. We had overall accuracy of 90%, which is very good. But, model's not perfect. It breaks down, for city names that are colliding with each other, same city names for different states. So that's why we had some of the inaccuracies. And we like to apply this model to the 2020 election as well. And we're in the process of gathering that data. Hopefully that will complete before the election completes. And we'll be able to get some results from that. So thank you very much, everyone.
Thank you very much for all the presenters. They are very interesting, and we have a lot of different topics and so on. So as planned, we'll have 10 minutes of break. You can call it a coffee break or tea break. And so we will resume at 10:50. 10:50. Stay tuned. And the next talk will be given by Professor Nicole Vincent. Do you see the screen here?
Yes.
Good. So Professor Nicole Vincent is a professor of artificial intelligence and computer science at the University of Paris, and former head of the Intelligent Systems and Perception team, associate editor of the Pattern Recognition Journal, and also Professor Camille Kurtz, and he is a lead researcher in artificial intelligence and computer science at the University of Paris. So we will resume at 10:50.
Hello. I hope we hope you are all well. And here we are, myself, Nicole Vincent, and Camille Kurtz. As you can see, our first name, Nicole and Camille, are possible names for females. And besides, when you are looking at us, you see that Camille has long curled hair, whereas I have only very short hair. So it's difficult to find the gender according to these two characteristics, either in the textual part or in the image analysis. So I am wondering if the characteristics are always so difficult to find.
Yes, Nicole, this is totally true, and this will motivate our talk. Features are really hot part of pattern recognition, and in the different disciplines of ICPRAI, we all agree on the importance of the field. For instance, if you search for the word feature in the proceedings of the ICPRAI conference, you can find more than 1,400 instances of the word features. And for the last decades, numerous words to build features that are efficient were proposed in the literature. And according to the different disciplines, the nature of the data may differ. In this talk, we focus on image analysis, but the generalization is quite obvious. For instance, 1D or 3D signals, and cloud of points, or even on videos. But why we decided to focus on image, Nicole?
Oh yes, we have focused on image because the structure of the image is quite particular. It's an array of numerical values, but that involves the description of the spatial relation between the different elements. And besides, it's a discretization of reality with different aspects of this reality thanks to different sensors, so such as colors or depth. And there is another important reason to analyze image, because image are intermediary medium in many domains, in physics for simulation, or more nearer to us in speech analysis. As you see in the middle of the illustration, some image in time series and even in text. On the right, you have the illustration of a text thanks to the reading, thanks to an automat. So you see, in an image, in an array, in a 2D array, a pixel is the atomic primitive. Nevertheless, it carries too little information, too local information, and generally it's not sufficient to have directly some conclusion. But you see, I have introduced the term primitive, whereas till now we were speaking of features. So is this very important to change the names like this, Camille?
Yes, so before to go further, it is necessary to provide some vocabulary. Depending on the communities, different words are used to denote the notion of feature, for instance, characteristic, primitive, or descriptor. And in this talk, we keep the general notion of feature. And in reality, features can be combined in a descriptor, or feature vector, or hierarchy, or even associated with a codebook. This depends on the task. And features are really often relative to different primitives, such as pixel or superpixel, as illustrated here on the right image, where we computed superpixel from the building of Université de Paris. And they can be also relative to regions of interest. So, where can we find features in the pattern recognition system?
In fact, in a global system in pattern recognition, you have an input and an output, and in between, you have all the processing. Generally, when you speak of feature, the standard understanding is to consider only the core of the processing and to omit the pre-processing and the post-processing. But in fact, these are very important parts. In the pre-processing, for example, you do binarization, and for this, you consider the pixel color, for example. And in the post-processing, you have some regularization. So features happens to be everywhere, but in different parts. And are they always for the same purpose?
So features are used and are considered in a lot of different tasks in pattern recognition. We provide here and after a non-exhaustive list. Features are really often used to have a description of the visual content of a scene, and they are used to model a reality, for instance, to get an approximation of concrete world and to generate models. They are also a base for reasoning along the process, and they can also be used to learn correlations between different views or to define similarity measures. In the example presented at the bottom of the slide, you can see some points of interest that have been extracted from images. These points are characterized by different features, and then these features are used to match the images to provide as output a panoramic image alignment. So now we can also study who are the users of features.
Yes, because there are several points of view. In the beginning of the elaboration of the system, there is an expert that is observing the image, and he wants to describe the image. But of course, he has not an objective way to describe the image, because he has in mind the results he wants to find. So the causalities between the features what he is describing and the results is important. Besides, sometimes he wants some real-time process, so he has some execution time constraints in mind. Then, from the data scientist point of view, the first thing is to base the features on the expert description, but in the same time, he has the data scientific as a goal, that is simplification of the real world, in order to use mathematical theorems that will enable him to have some reasoning to go from the input to the output through the description, thanks to the features. And finally, the developers are more involved in taking account the memory size and the execution speed. But all define features, but do they have the same approaches to define these features?
Actually not. We can distinguish in the literature two main families of features. So uncrafted features that are more closer to the end user need, and automatic features that are more related to the data scientists. So to define and to design new uncrafted features, the end user can use his expertise regarding the content of the image to define some important characteristics that are discriminant. On the other side, the automatic features can be directly learned from a set of data using end-to-end learning procedures. And if you query in Google Scholars the term features in pattern recognition versus the query deep learning pattern recognition, you can get these two results. So you have on the abscissa the year, and on the ordinate you have the number of publications. So you can see that the blue curve is growing till 2014 and then starts to decrease, while in parallel the red curve continues to increase. But we can also say that the distinction between handcrafted versus automatic features is not always well justified, because we can say that all features are handcrafted. Indeed, even if automatic features are automatically extracted from the data, it is first required to design the architecture, for instance, a CNN, to extract these features. So actually, these features are also handcrafted, and the problem is just moved. So we'll now provide you an overview of features, and we'll first start by the primitives.
Yes. Before defining the features, we have seen that we must know on what element they are defined. And the pixel is the first obvious primitive. It's a 2D, 0D primitive. We have already seen it carrying two local information to solve all the problems. More sophisticated primitives can be considered. 1D primitives, for example, straight lines or circles, or 2D primitives. These can be disk or patches or field regions with very irregular contours. On the right, you have an illustration that shows initial images and a classification that is performed in the second row according to a pixel classification, and in the third row about region classification. We can see that, for example, in the region classification, some regions are better recovered, such as the river, that appears to have a low number of connected components compared to the red elements that were in the pixel classification. So the choice of the primitive depends, of course, on the task, on the objective, and on the application. Maybe we can give some examples to illustrate this. And first, we can begin with a zero-dimensional primitive.
So pixels of points are the historic primitives. They have been considered in many applications for various tasks in computer vision and pattern recognition. And they have been used because they are really close to the image representation, the matrix, and they are also very close to the sensor. So on this illustration, some points of interest are extracted from an image from Notre Dame de Paris, and such points of interest can be extracted by considering different features such as shift or surf. And once these features are extracted, they can be characterized by additional information and can be further used to compute some matching between pairs of images. So these points often rely on salient points. And we can now see an example, Nicole, of one-dimensional primitive.
Yes, it's quite interesting one-dimensional primitives because you see they can model 0D primitives as a pixel. It just can be considered as a straight line segment with length 1, and in the same time it can approximate field form. As a field form can be seen as a juxtaposition of parallel lines covering the field form. then you have something that you have a unity in the primitives that enable to approximate any image. And besides, you can consider the direction of the straight line segment if you need to. You have an illustration of a document that is approximated with a straight line segment with different lengths. With the short segments, you can consider the character level, and with longer straight lines, you have the line segments. So that's quite interesting to have 1D segments, but maybe 2D regions could be interesting.
So regions are a really good example of two-dimensional primitives. So they have been mainly used for object-based image analysis in different disciplines, and they are used to approximate file forms corresponding to regions of interest. They are also very close to the human perception of the content of an image, because we think in terms of objects and interaction between objects. To define regions, you need first to segment or to partition the image using a specific algorithm. And such algorithm is based on different features to measure the region homogeneity. And another advantage of two-dimensional primitives such as regions is that they enable a new level of reasoning for features. For instance, in the example presented at the bottom of the slide, you can see on this image a segmentation, and on the right a specific region. And from this region, it's possible to study the neighborhood of it by computing, for instance, a region adjacency graph. So we presented here some example of primitives, and we'll now discuss the way the features are represented.
Yes. In fact, before we give some example of features, we must see what are the representation structures that can be used, and we have sorted them according to their complexity. The most often used representation is a vector space. And this vector space can be in 1 or 2 or many dimensions. So in a 1D feature vector, you have characteristics that are associated with the component of the vector. Using a 2D representation, you can have vectors that respect the image nature. And if you use more than 2 dimensions, you must use some tensor structure. In any case, you have to limit the dimension of the vector feature vector because of the curse malediction. When you use vector space, you are inclined to use linear transform because they are the best suited transform associated with vector space. But sometimes this is not possible. This is not the case in reality. Then you can use a string. It enables to get rid of the number of features, and that can vary. But then you have to find new computation tools, such as an edit distance, for example. With graphs, you have richer information, but also more difficulty in handling these structures, as it's quite difficult to have an efficient graph isomorphism to define. And so, actually, when using graph, many studies are embedding it in a vector space, in various vector spaces. And it's the same with deep learning on graphs. Finally, you can have bags of words if you have no structure, where you have no structure. But here too, we usually you have to come back to a vector space thanks to an histogram. So I have not quite answered to your question about features, but maybe you can enter in the features themselves. Oh, sorry.
So features are really various, and they enable to measure a lot of different information. We usually sort them by their order. A classical example of first-order features enable to measure the color, the texture, for instance, to describe my curly hair, or the shape to discriminate the size of Nicole versus mine. First-order features can be single-valued. They can be also descriptors involving the decomposition of the image in a basis, for instance, Fourier coefficients or moments. In the example at the center of the slide, it's first-order features. These first-order features are related to texture. Here, starting from a Ritz filter bank, so a basic bank of filters, we use a support vector machine to learn a linear combination of these filters to build a more rich filter that enable the detection of particular visual elements in medical images related to pathologies. Really famous features also are Hogg or Sift and Better. First-order features can be local thanks to linear kernels or thanks to non-linear kernels using, for instance, support vector machines. Then the second category are second-order features that they enable to consider the correlations among the grid levels in the images. From the co-occurrence matrices, you can easily derive arallic features. A more recent example is the covariance descriptor unit proposed in the CNN architecture. And spatial relations are also a good example of higher order features. And now, Nicole will introduce you the concept of covariance descriptor units.
Yes. So in the CNNs, you have the first part. For example, here, the blue part that enables to find features. But you can also add, after this computation of feature, covariance, and these features can be learned directly. But this, to improve the results, you can compute the covariance matrix of these features and continue the system till the output with new convolution, 1D or other convolution. And this covariance descriptor unit has quite a lot improved the results of the CNN architecture. It's much more complicated and has to have easier computation, but it's quite an interesting new proposal. But you also spoke of spatial relations that are quite interesting, that are older but quite interesting.
Thank you, Nicole. Yes, spatial relations enable to quantitatively capture the relative position of objects in image content. On the illustration on the left, you have different objects. You have a dog and a tree, and spatial relations can be used to evaluate the relative position of the dog related to the tree. So, for instance, the dog is at the top of the tree, or left of the tree, or the right, etc. Historically, certain relations were proposed by Freeman and Rosenfeld, topological, geometrical, or directional relations. More recently, we proposed in a previous work the concept of spatial enlacement descriptors that enable to capture more complex spatial relations. On this example here, you have a complex relation between the black object and the gray object. It is a surrounding relation. And then on the middle, you have here a relation of enlacement, while on the right, you have a situation of complex interlacement. And it is possible to compute a descriptor that enables to capture this kind of relation. In this example, this is a directional approach, based on ray tracing, and the idea is to compute the number of points in each segment of object A that interlace with object B. And the resulting descriptor is an histogram enabling to evaluate the enlacement relation in different directions. So in this part, we mainly focused on the computation of features, and they're designed for one image, for one source of information, but it is also possible to deal with multi-source.
Yes, and in fact, we nearly always have multi-source data because a color image has 3 channels, for example, and so we deal with 3 sources of information, and this is more obvious with hyperspectral data from remote sensing, for example. In the medical image, it's certainly different. You can have images that are related to the anatomical aspect of the patient, and you have also functional images, and you have to deal with different sources. More recently, with smart photo acquisition, they provide a burst mode that enable to have several still images that can be considered as different sources of information. And of course, video processing also can be seen as having multiple sources of information. And if you have different images, certainly you want to consider different families of features. And maybe they can also lead to different representations because they are computed thanks to different transforms. One solution to deal with this is to use, for example, a multipath CNN. But I think that if we really very often use multiple data sources, we also consider when having a color image to process the image in a gray level. So we could have a question that is it always efficient to leverage multi-model data?
Yes, this is a very good question. I think in any case, you have to check carefully if the data carry complementary information that is not too redundant. So to this end, you can discuss directly with the experts of the domain to assess with him if the different data are complementary and if the different sources of data are relevant for a specific task. But you can also try to do it computationally by using the answer of your pattern recognition system to check if the latter is improved by adding new sources of information in the system. So on this example, an RGB image here is coupled with LiDAR data that measures the depth for autonomous vehicle segmentation. And this enabled to improve the system since the two sources of information here are really complementary. But now, Nicole, in practice, how to deal with multiple sources of information?
In practice, you have to fusion the information coming from the different sources. And this fusion can be done at different levels. At the data level, if the data are of the same structure, or if there are images, we can have some registration. For example, it needs some registration. But it also can be done at the feature level or at the decision level. It depends on the application and on the diversity of the information sources. Here on the illustration, you have two sources of information. One is a sketch or an image, and the second is textual. Of course, you cannot have a fusion at the data level, but thanks to different computation of features, you can embed the two within a vector of features that are common. So that's the way an aggregation of features can be done. It can be done easily, more easily than here when you just concatenate the vector of information. So we have seen different types of sources. Is there any other multimodal sources?
Yes, here I will present you an example of multi-source data, here with multi-temporal data. On the right, you can see a satellite image time series. This is an image sequence representing a particular landscape. Here, this is agricultural crops in Holland, and the different images have been acquired by the same sensor at different dates, here in the month of April. And along the months, you can see that the agricultural crops are changing and some red crops appears. Actually, they represent the tulips. So when dealing with image sequence classifications, two dimensions are essential, the spatial one and the temporal one, and they carry really complementary information. And we can aim to mix these different dimensions to provide richer information to the decision-making process. Various applications can be considered, for instance, video, 2D plus T medical images, and remote sensing. And such data can be considered, as they are 2D plus T, they can be viewed also as a data cube. And state-of-the-art approaches for image sequence classification mainly rely on the use of a 3D convolutional neural network for the classification step. But in practice, this is very difficult to use 3D CNN to classify image sequences because they require a large amount of training data. And in several applications, these data are not easily available. But maybe, Nicole, do you know another strategy to deal with this data?
Yes, I think we know. As you say, we have 3 dimensions in the cube, but 2 dimensions are related to space and 1 to temporal information. With the 2 dimensions of space, maybe we can try have only 1 dimension for space, and this can be done by indexing the pixel of one image thanks to space filling curves and considering the linear abscissa on the curve. So in the left, you see the different pixels that are numbered, and in one image, the first image, for example, and the value of the pixels can be used in a new 2D representation and put on the first row. Then each image of the sequence can enable to fill 1 row in the new representation that is a 2D representation. That's quite interesting because now with this new spatiotemporal representation, you can use some classical 2D CNN. In order to make you better understand what is done using this way of transforming the data, we are showing you here in the middle, you have a cube, a set of images that are all representing the same spatial domain all along the curve. And to see what is really in the space, we have a Google Earth map here, image that shows you the spatial representation. To better understand, we have not used a space filling curve. We have only represented here one part of a possible curve, And this part is considered on the yellow segment. We see that this yellow segment passes through a forest, a urban part, and 2 meadows. On the right, you have the representation. We have said one date is one line. So the image that is presented at the top of the cube is associated with the dashed line, the yellow dashed line on the right. And you can see that on the left, you have the forest, and you can see the behavior of the forest all along the year. The red part is indicating the chlorophyll. In the middle, you have what is the evolution along time of the urban part, And on the right, you have the 2 meadows. They are not exactly the same, and you can see, for example, that the meadows have not been mowed at the same time. So this is quite a good representation, a very good summary of the cube in a 2D representation. But in fact, here, it's a data level fusion. And I think that, Camille, you have examples of much more complex feature level fusion.
Yes, Nicole, thank you. In this example, we now focus on feature aggregation for a particular task. Here, we aim to build hierarchical image representation. So a hierarchical image representation can be modeled as a tree, and each cut of the tree models the image at a particular scale. And usually, such kind of tree, here this is a binary partition tree. So usually a binary partition tree is built for one given image and one given feature. So such feature enabled to provide the merging order of adjacent regions. And in this study, we aim to manage multiple features within the binary partition tree building process. And to this end, we use a particular feature aggregation strategy that relies on establishing a consensus between the different features. Note that the different features can be extracted from only one image or from a set of images representing the same scene. And the consensus enables to select which will be the next pair of nodes to be merged to construct the higher level of the tree. So we provide you some example of multi-source imaging and some way to build a feature from this kind of multi-source data. And we'll now talk in the next part about features properties.
Yes, that's quite an important point, because when you are choosing the features, we must have some criteria. We have spoken of some, but historically, the properties of invariance were very important, as the description must be invariant towards a group of transform in order to be robust enough to some transformation. The locality is also important. It depends on the primitives we have already spoken about. The constraint of storage and speed are important, but nowadays there are emerging some aspects of the primitives that are the semantic aspects, the interpretability of the whole systems that depends on the feature, and the expressivity of the features that are used in order for the end user to understand what is done. But I see that time is going on, so I think that Camille, you can speak about semantic.
Okay, so just a few words about the semantic properties of features. So first, what is semantic? So it's a very subjective notion, and this notion is used to designate some visual concepts that appears in the image content. And this semantic can emerge from the image content at different levels. So we can say that an image has many semantic contents. And in this example, so on the bottom of the slide, on the illustration at the top, we consider the task of a content-based image retrieval for medical imaging. And in this work, images of the database were described using sets of semantic terms. And these semantic terms were related to the visual appearance of the lesion in the image. And here, the goal is to try to combine visual information and semantic information to build a term dissimilarity measure that can be used to enhance the retrieval process of similar images. And this term dissimilarity measure relies on two kinds of information. So first, visual information. So here you have the texture model that are used to predict the semantic terms. And if you want to evaluate the visual dissimilarity between two terms, you can just compute the distance between their visual models. And on the other side, you can also extract semantic information by computing some dissimilarity measures between the terms in the ontological structures. So this strategy enables to enhance the retrieval step of the system. And now time is running, so we'll switch to the next part, Nicole, and we'll now discuss about how to select and to optimize the features.
Yes. When you are defining the features, you say you are extracting features. And in fact, you are optimizing everything involving the properties we have seen just before. Most often, we focused on results, on improving the results. The difference between optimization and selection is that in the optimization and the definition of features, the search is done in a space generated by fixed processes, while in the selection, you are also performing optimization, but the search space is limited to the initial set of features, and the aim is to decrease their number. Maybe you can be more precise on the selection.
So yes, as mentioned by Nicole, the selection is also an optimization, but the search spaces are different. So given an existing set of features, selection strategy aims to pull the more relevant features for a given task. And this is performed without modification of the initial features. And two different strategies can be considered. The first one requires to set a priori the number of expected features. This can be done, for instance, by using transfer learning or by considering pooling strategies. And more recently, in CNN architecture, the use of class attention map has been proposed. So given the answer, the decision of a network, it's possible to derive which features were the most relevant to lead to this decision. On the example on the right, we provide a class activation map of the spatial-temporal representation of remote sensing images presented earlier by Nicole. And here, the attention map enabled to select which time range was the more adapted here to classify the vineyards. It's also possible to consider other strategy where the number of features is selected a posteriori. Various families of strategy were proposed in the literature, for instance, forward or backward or wrapper, or strategy relying on random forest or machine learning. Nicole will now present you an example of a strategy based on machine learning.
Yeah, we say we are selecting features, but in fact you can do better to have more diverse and non-redundant features. To each feature, a classifier can be associated based on a single feature. And from this classifier, we can thanks to genetic algorithm, evaluate the subset of classifier thanks to a fitness function, and have in such a way an optimization in order to have a selection. But optimization of feature is a quite different approach.
Yes, the optimization is different than selection. Optimization strategies aim to build novel features from the existing features, and these novel features they have to be more discriminant for a particular task. Different families of approach coexist in the literature. It's possible to directly use an existing set of features. PCA is a famous example where you can build from the existing set of features, novel features from a linear combination, and you can easily build a few features that capture more than 95% of the discriminant information. Fisher's linear discriminant analysis can be also considered or genetic algorithm to learn parameters of the model. More recently, optimization-based procedures were used to directly learn optimized feature from a set of training data. This is the case with CNN, an end-to-end learning procedure. But we can also say that dropout is a step of the optimization procedure to get better generalization properties. Generative models such as GAN can be used for data augmentation. And finally, it's also possible to consider several objective CNN architecture, as in the example at the bottom right on the slide. Here, from a set of images representing faces, the main objective is to score the beauty of the person. But to optimize the features of the beauty, it's also possible to add additional objectives, such as here a gender classification or an ethnicity classification. And by adding these complementary objectives, it's possible to optimize the features related to the beauty score. So, well, it's now time for us to conclude.
Yes, and we can say that features are more than ever in the core of research. And we have seen so many new architectures to be proposed and to be found. And we also see the fact that many new resources are given to the community and can be reused in order to have good trainings and to have a transfer from one domain to another, with some fine tunings. The data initially that make difference for training was ImageNet, and now we see equivalent sets for videos, for example, and in many other domains. A second point we can highlight is the need for mathematical research in order to enlarge a variety of structures that are used, for example, manifolds and graphs, and to develop nonlinear filters in order to have more tools to use. So we can say that from this we can say that the last year have been quite productive, don't you think, Camille?
Oh, this is a very good question and maybe an open question. We can reformulate this question differently. So what's new since David Marr? What's new since the Gabor filters? For sure, now we have some powerful architecture to learn linear convolutional features at different scales. And maybe this is the main novelty. But we continue to mimic the human perception. So what will be the next big step for the PRAI community? And we have to think about this. So in conclusion, we can learn to do with what we have, and we hope the whole PRAI community will increase what we have. So this concludes our talk, and we thank you for listening to this talk. And if you have any question, we'll be pleased to answer to you. Thank you.
Thank you very much. So thank you for giving a very excellent talk related to different types of features, their structures and ways of optimizing them. Would like to conclude the program for today, but tomorrow we'll have keynote speeches related to medical image processing and also writing in the air, how to recognize writing in the air. So these are very interesting talks apart from presentations of oral and video. And again, if you are interested in all these papers, proceedings is available at our website. Just click proceedings. And if you want to look at the program for the last day, you can click registration, and inside you will see the content of the musical webinar with the songs and the singers, etc. So finally, we would like to thank our keynote speakers again and all the presenters of the papers for today. Thank you, and see you tomorrow. And thank you, Nicola. Thank you. Bye-bye.
Bye.